get branch. What's that search? Amazing tired of lowercase d. And then the name of the branch. Then uppercase d.
No.
Cool.
Yep.
We will have to change branches if there are new branches we're trying to do.
Just switch into VS Code. Missed it by a minute.
Oh.
Thank goodness.
Missed it by that much.
You guys have an unrealistic expectation.
All right. Good evening, everyone. Let's go ahead and get started. What's up with that? Everybody is like way behind. Sorry, I started with this.
We just don't want to be.
Not personal.
Just business.
Just business.
Like how they do in the movies, they're going to kill you, they go, it's not personal.
Yeah.
The learning's better back here.
Oh, really?
We've always been here all day.
Yeah. All right. So welcome to week 22 of 24. All right.
And you're going to cry when we're gone?
I'm going to cry.
Are you going to?
Yeah. I'm gonna miss you guys. Yeah, you guys wanna come back for the next week? Well, I hope not. All right. So before I begin today's lecture, let me again share the same information. So this is week 22. After this week, we have 2 more weeks, or I would say 1.5 week. I say 1.5 week because the last week the class or the session ends on Tuesday, so there's no Thursday class. So week 22, this week is going to be the last week of any kind of lectures or any kind of introduction or anything related to the syllabus. So by the end of this week, which is Saturday, everything that's in the syllabus or whatever the course content is going to be done. Okay. Week 23 and 24 are going to be completely project work. Okay. If there's any review or anything, I'll be here. Let me know. We can go over it on today, and then week 23 and 24 every Tuesday. You guys remember there's a submission due, and till now only one group has submitted anything to me, unless you guys submitted some to the TAs. That's different. Okay. So so this Tuesday, the next Tuesday, then the following Tuesday, there's a submission due. We'll talk about it towards the end of the class. For today, I'll just some of the actually only since one I have submitted, I've only seen one submission. So I might call upon, just to share the information. It's not anything to do with the grading or anything. I just want, I've seen some of the good points, so I want the other groups to share that information so that, everybody can be aware what's going on. Okay, but we'll discuss that towards the end of the class, whenever we get done with today's lecture. Okay, and then I will also talk about, remind me if I forget, what's due on next Tuesday. Like, what do you guys have to show next Tuesday? And the last Tuesday is, of course, the final presentation. Okay, any questions? Good. So today we are going to look at algorithms. And so those of you who have computer science background or computer information background, this is kind of taught in the first semester or the first 2 semesters, like CS 101. What this is, these are kind of basic algorithms, and we'll go through what those are. Before we look into anything, just Google the word algorithm and see what it means, and then we'll go ahead and discuss that. Okay, take like a minute or two and just Google that word for people who still kind of confused what it means or not completely from that background, and then I'll go through them. We'll discuss what those are. Okay. Okay. As you find the meaning of this word, please go ahead and share. Kind of just raise your hand and let me know what you guys found, so that we can build upon that information. What is it, Andreas?
The example, yes, it's like a recipe.
Okay. Example is a recipe. Why are they giving what's before the example?
It's a set of rules.
Set of rules. Okay. It's a process.
Instructions for a computer.
What was that? Instructions for?
Like instructions for a computer to do something.
Okay. Okay. Anything else? Eric, what do you think?
It's an alligator with rhythm.
Alligator with rhythm. I like that. Alligator with rhythm. Wow. I have no idea what that means. I think I spelled it correctly. That's a nice one. Include that in the and just say, hey, algorithm is alligator with rhythm, and then we're done. Yeah, Eric, did you find anything different from these?
Eric?
Eric.
Okay.
Sorry.
Well, the definition that I found talked about how you can calculate data processing and automated reasoning.
Okay. Calculation and reasoning.
Uh-huh.
Automation. Okay. So all of these are correct. If I'm taking like a basic level definition, algorithm is basically a set of steps. Okay. Anything that you take steps to solve a problem, that's what an algorithm is. Andreas mentioned a recipe. It could be as basic as that. Let's suppose I want to make a sandwich. I want to make a PB&J, all right, peanut butter jelly sandwich. So what are my steps, right? I go to my fridge, open the fridge, all right, take out peanut butter, then take out jelly, Open peanut butter, open jelly, spread peanut butter, then spread jelly, make a sandwich, right? Take out the bread. So these are the steps, and the result will be that I will have a PB&J sandwich. Okay, that is considered an algorithm. That's what it is. All right. Instructions for computer. Now this kind of ties into that you are telling the computer what to do. You are defining a set of steps that a computer will perform, and that's what we call an algorithm. Okay. Now this could be as simple as a recipe. It could be as complex as sorting an array, coming up with some calculation. Okay, searching. Okay, searching through the database, searching through an array for something particular, for a number, let's suppose. That's also an algorithm. What are the steps you're going to take? Okay, so that's the basic definition of an algorithm. All right, David, you missed the definition of algorithm. Algorithm with rhythm. That's the definition of.
That is absolutely correct.
That is.
Perfect.
Yeah. From all of these, alligator with a rhythm. So anybody asks what an algorithm is, it's an alligator with a rhythm. That's what it is. Okay, so it's basically a set of steps. All right. Now, when it comes to computer science, what we do is we try to solve a problem. So an algorithm is basically trying to solve an issue. And trying to solve that issue more better. Okay. Now, what I mean by this is that you will find a same problem and you will find different solutions for it. What this means is that each solution, what they do is they try to come up with a better algorithm. Okay. I'm able to solve the problem using algorithm number 1. Can I make it better? And then there's a second algorithm. Can I make it even better? Then you have a third algorithm. So these are kind of steps that you're trying to solve a problem more efficiently. Okay, that's why you will see, and I'll introduce you. You will see multiple algorithms for the same problem. Okay, and each one is building because they want to try to solve the same issue but with more efficiency. Okay. This. So the two set of algorithms that we are going to look this week is searching algorithms and then sorting algorithms. Okay. Today we are going to look at the searching part. On Thursday we'll look into sorting. Okay. What does searching means? Searching means that you are given an input. In this example, today our input would be an array of integers. Okay. It can be anything, but this is, if you understand this logic, it's kind of translates into everything else. Okay. And this is the basic example. That's where we start with though. Okay. So we're going to be looking, we will have an input array and then we will be using some algorithms to search through an array. Okay. Now I can have, let's suppose I have an array of 10 numbers, 20, 30 numbers. I'm trying to find a number within this 30 elements. Okay. For example, let's suppose my array is 3. This is my array. I have numbers 3, 5, 7, 10, 15, 20, 25. Okay. Now, my problem is, the statement is that I want to find 15 in this array. Okay. I want to find the number 15 and I want to return the index number. So this is my 0, 1, 2, 3, 4, 5, 6. Okay. Now my answer is at index 4, I have 15, and that's the solution. All right. Now what it comes down to is, for us humans, it's kind of easy to see, but how do we tell the computer? All right. How do we, when this is given to a computer, how do you tell the computer that, go through this, define a set of steps, go through them, and find this number for me? Okay, and that's what an algorithm is. That you put some steps over here, create an algorithm that will tell the computer how to go and search for any number. Okay? Let's see. All right. Any questions on the concept? Yes.
Pretty much just like the bubble sort that we talked about a long time.
Exactly. Yeah. Yeah.
Just make it more-
Yep.
Is there like a, I don't know, like a repository of known methods or
Yes.
that's being worked on?
Mm-hmm. Yeah, I'll show you. So as Gabriel is saying, it's like something we saw, bubble sort, right? That qualifies as an algorithm, one of the algorithms for sorting. We'll look at it on Thursday. Okay, and that's correct. But today we are focused on searching, so we are going to look at just the searching ones. And we'll see. We'll look at a couple of searching algorithms, and then we'll determine what are the best ones and why do we say that these are the best ones. Okay. But at a high level, right? If you have an algorithm, what would you say is the best one? So algorithm is the steps that you take, right, to solve a problem. What would you say is the best algorithm? So I have one algorithm that takes 15 steps to solve the same problem, and I have one that takes 10 steps to solve the same problem. What would you say is the better? Mm-hmm. Yes.
Does it depend on how long it would take to implement the algorithm?
No. Depend. So Dylan is saying it depends how long it takes to implement that algorithm, right? So that's like a time constraint on the programmer, on the engineer. So that's to come to these algorithms, the sorting ones, it might have taken years for somebody to figure it out. But the efficiency is still measured how fast the algorithm is and how quickly it completes it.
What
Yes.
I mean is like, let's say it takes some time to set up the algorithm and code,
Okay.
but overall it's a lot faster, which would be good for a large application.
Right.
But something like bubble sort might be faster to implement because it's a lot faster to type out real quick.
Mm-hmm.
If it's a very short thing you're trying to sort.
Okay. So again, use the word shorter to type out. So these kind of have, it's not, if it is, you have 100 lines of code or 50 lines of code. Okay. This doesn't necessarily mean that my algorithm is 50 lines of code. It kind of is faster. Okay. It has, it's not based on that. What is it based on is how quickly or how efficiently it processes that information. And we'll see what it is and how we measure those. But it has nothing to do with the lines of code. This might be more efficient than this one, even though this has less lines. Again, bubble sort could be difficult to implement, as in difficult to remember or difficult to type out the code. But it doesn't mean that bubble sort is, worse than some of the other ones. Okay, we'll see what the measure and how do we benchmark. Did you have something? Go ahead.
I was going to say it's execution or runtime.
Yeah. So implementing that algorithm is just a one-time effort. So that's why once you implement it and it's done. Okay. What this is the repetitive part. This is what we should be more concerned about. Okay. Good observation. Good question. Right. Hopefully that clears. All right, so let's look at the first one. Let's start with the basic one. Okay, so I want to search 15. How would I search 15? Just a rudimentary, that's a basic one. So the easiest one right now would be that I start from this one, start from my first location, and I check, is this equal to 15? Okay, and I say, oh, it's not. Okay, then I move on to the next one. Then I check if this is equal to 15. No. Okay, then I move on to this one. Is this equal to 15? No, then I move on to this one. Is this equal to 15? No, then I move on to this one. Is this equal to 15? Yes, and that's my answer. Okay? This is called linear search algorithm. Okay? Again, in linear search, it's linear. It goes one by one by one until it finds that element, or it reaches the end of the array. Let's suppose I want to search 26. It will go through 1, 2, 3, come here, end of the array. It will say it didn't find it. So it will say false or did not find it. Okay? And this algorithm is called linear. And linear, you can imagine why, because I'm going in a straight line. Okay? What is the pattern that you guys see over here? 3, 5, 7, 10, 15, 20, 25.
Increasing numbers.
Increasing numbers. These are sorted. Okay? Alright, take note of this. What if my numbers are not sorted? There are 5, 3, 25, 1, and I still have, let's suppose, 10, 15, and something. Now these are not sorted, okay? In linear search, if I begin, my 15 is still on the same position. I will still start from here, go here, 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 and I will find this number, okay? We'll see how important this is right now, but you guys guessed it right that there's a pattern to it right now, okay? Now what am I doing in my linear search is, okay, before I go into the coding part, any questions on the linear search? Can everybody get it? How we are searching, we're starting from the first one going to the end, or until we find the number that we're looking for. Okay, now how would I implement this in my code? Yeah, good. For loop. So what I'm doing is I'm starting my loop which goes from 0 to the end of the array. Right now I have 6 elements, so it will go up to 0 to 6 less than, so it will stop at 5. Okay, and then what I do is I am checking that the element at this index, which index? This index, okay, let's say I, is equal to the number that I'm searching. Okay, and I keep going through this loop until I find that number or it reaches to the end of the array. Okay, that's the coding part. Okay, so okay, and this is my number to search. Okay, and I'm also passing in an array. Okay, so this is the array that I'm going to search and the number that I'm going to search. All right. Any brave soul wants to come up and kind of complete this function? Take a stab at it. This is probably the easier one that we are going to see today or Thursday. Anything before he completed, I already had this credit bracket. Yeah. So somebody wants to come up and take a try and see how we can implement this. I already gave you the steps. You have to write a for loop that goes through it, and then you have to check, which is an if condition, and return false or true. David?
Yeah, right.
Come on, give it a try. What's the worst that's going to happen?
No.
What's the worst that's going to happen?
There's infinitely smarter kids who can.
No, I believe in you. You can do it. Give it a try.
I'll Google it for 20 minutes.
You can. Okay, here's. You can just write it in English also. Just the steps. Huh? Dylan, you want to try? I heard Dylan saying. All right. Well, I have a more difficult one for you. That's why I don't want him to come up. This is relatively easier. That's why I wanted somebody else. All right.
You guys will be my auto.
Yeah.
Just hit tab. Just write tab.
Yeah. Intelligent.
Tab. So it's a smart way.
All right. So,
So do 4 and then put in parentheses tab.
yeah, it just auto completes the entire time. I'm so used to it. So we have to pass in the array. So 0 or hold on. Already blundering here. So I equals 0.
Okay. Yeah.
Was it semicolon?
Yeah.
All right, and we're off to a good start. If I is less than array dot length.
Yep.
And then semicolon I plus plus. Then there's like a curly bracket there.
Yep.
And then we have an if statement, right?
Yeah.
If let's see. What is number search again?
This is the number that I want to search. So over here,
Oh,
this is
I see.
15. So this is my array.
Oh, I got you.
All right. I want to search 15.
Okay, so if can you guys see? I feel like I'm like
Yeah.
Good.
If number search.
if right num search is equal to I guess the index.
Yeah. So I'm going to compare against this element.
Okay.
So how do you access the element of the array?
Array I.
Yes.
Yeah. So ARR I like that.
Yeah.
Then you're done, right?
That's it. Yeah.
Then what? Do you just console log or?
Yeah. You can do a console log.
I'm just gonna do console log found it. Okay. Then and then else we would have to keep searching, I guess, right? And that's pretty much generally it. I don't know how how long you want me to keep going. But
Well, it should go on until it finds it or it reaches the end of the. So you're almost done.
okay. Um,
So let's say you came here, right?
yeah.
And you search, you said, oh, it's false. I mean,
So
it didn't
else
work
it-
out.
Else it would have to say false, right? Or I guess else if, or yeah. If num search.
No, just run the search again. Revolution.
What if you don't do anything? What will happen? It comes here, doesn't find it, goes back here.
Oh yeah.
Keep going. Right?
Yeah. It should just keep going, right?
Yeah.
So I don't have to run the function again, right?
It's already, you are inside the for loop. The function will keep running until this thing.
Okay.
So you don't need anything else actually.
Oh,
So what will happen is it will come, it will see, oh, does it match? Nope. Go back to the loop.
Oh,
Match? Nope. 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 Match? Yes.
Until it finds it. Yeah. Okay. I guess. I
So
don't-
the more what you can do is after console you can do a return. So as soon
Oh.
as you find it,
So it doesn't
just return.
Yeah, I got you.
Doesn't it just like stops over there, returns it, and that's it.
Yeah. Return.
You can close the if statement, and that should be it.
We'll just that down there.
Yeah, this is for the for loop.
Yeah.
Oh, where's your for loop at? Oh, you need one more, but that's okay.
Do I?
I think that was a function. And
That has this, right?
well, that's a function,
Oh, that's a function. Oh, crap.
so you can put one more. That should be it. Yeah. All right. So that's the linear search. All right. Any questions on the coding? Any questions on how we solve this? Okay. So these kind of solutions, what we call them, and you will hear the word is brute force. Yes.
If we want to put something that.
What was that?
If we got all the way through the array, we
Yeah.
put something that said not found.
Yeah.
Or does not exist.
So you can change this up a bit. You can say return true, and then at the end of the program you can say return false. So as soon as it finds it will return true, and this will end. If not, if it comes over here, this means you have not found it. So you can say that. If you want a string, you can still do this. Come over here, write a string also, that's also fine. Before the return statement, you can do a console log here and say not found and then return false. Okay. Now, what I was saying that we call this brute force. What it means is you are kind of like going through each one, and then trying to find it, right? So right now I have like 6, right? I could have more. Okay. So here's the question. What's the, Fernando, you tell me, what's the best case scenario? When I say what's the best case scenario in this search, what would be your answer?
Like best case scenario as for the function solving it, or best case scenario as in the best scenario where 15 would be the first window.
Right, and that is actually the correct answer. Well, because it's kind of vague what I'm asking, and you followed up with a question, and that's what you're trying to clarify. Always, I tell other people also, and I do the same thing. If they're kind of confusing, sometimes you will hear some questions that are vague and kind of intentional. So please make sure you guys follow up with the question so that you kind of clarify. So best case scenario, what I'm saying is from these numbers, which number is the easiest one to find? From these numbers, huh? 3. Yep. Why is it 3? Because it's the core. It takes only one step to find this, right? Basically, it's like right here. Okay. Now, if I say what's the worst case, what's the worst number to find? Huh? Yes, the last index, which is no, not infinity, n. You have a limited array. The length of the array is the worst one to find over here. Okay, and why is it? Because you're going to traverse through each one to get to this one. Right? And then when we talk about algorithms, we don't talk about saying, hey, the efficiency of algorithm is what's the best case. We always consider the worst case. That's how we measure the efficiency. Like how much time it's going to take the algorithm, what's the worst case that's going to take this algorithm to execute. And that's what we kind of measure the algorithms on. Okay? In this case, the worst case would be n. It will take the whole array to get to this one, right? Now, if my array, as I said, is n, it's right now it's like 10, 15, 1,000, 10,000, million. That's how much time is going to take to complete this process. Okay, linear search is considered one of the worst algorithms because it takes like so much time. It's kind of easy to implement again, but for the computer, it's super inefficient. All right, now how do we know it? Because from the worst case, we understand that it's going to take this much time or this much length of the array. Okay. All right. Now in JavaScript, they have some libraries that kind of helps you to measure the efficiency of the algorithm, and we call them benchmark. Look this up. They have a node module with benchmark, and it kind of times any algorithm that you put in, and it will time it for you. Okay. This has been this is on GitLab, or Nick and Will can go ahead and send you a zip file for this one. If you look into examples, run the npm install. I already did this, and it's going to install a node module called benchmark. And there are a few more, but all I want to show you is that you can use benchmark to kind of look through and find out how much time it is taking and what's the efficiency of this. All right. So in this one, we just put in our code for linear search, and it's going to execute this. It's going to spit out some numbers for us, telling us how much time it is taking. All right. This is 100 like 1 million. That's the length of the array. That's how many numbers I have. Okay, and it's going to run this benchmark and see how much time it takes. Oops. Yes. Yeah. Yeah. Okay. That's why you don't do ahead of before. Oops.
Yeah, very good stuff. You sure about that?
I remember the shortcut key to bring my terminal apparently not. Okay, so let's go ahead and run this. Benchmark examples. Okay. It probably throws you an out of memory error or something. Okay. Yeah, so let's go ahead and here's the increase the size of the allocation for our program. Let's drag this out. So you can use this, and this will kind of increases the allocated size for this particular program, and then it should be okay. Okay, so this is running for, and if this doesn't work on your computer, you can reduce the array. Right now, I showed you, right? We have like, I don't know, 1 million or 10 million or something. So you can keep reducing the number of zeros until it kind of executes. So this is what benchmark is. It will show you time and some other things. Look at the documentation again if you guys are interested. but I just wanted to show you that this is how we can benchmark and kind of figure out how much time the algorithm takes. Okay. Now again, these searching ones, they are not kind of implemented for like 10 or 15 or 20 or 100 or 1,000 or 10,000 numbers. These are being used for millions and billions and even trillion rows. Okay, so we need to consider those when you're looking at the efficiency. Okay, it's all about scaling. How big the data set is, that's what we're trying to achieve. Right, so let's look at the next one. There's a, this is a nice, let me slide this out too. This is a really nice visualization. It kind of shows you how these algorithm works. So right now we saw the linear search. So let's suppose I want to find 254 here. You can just type in the number and do a linear search. It's going to show you the animation. How do we proceed? And this is how it is going through, searching one until it finds the correct one. Okay. Okay. Let's look at the next one. So you guys see the issue with this, right? It takes a lot of time. It will go over here. So it's the, as I said, the definition of algorithm, right? You have a problem, you find a solution, and then you try to find a better solution, right? So of course people work on it, try to come up with a better solution because this doesn't work for larger data set, right? Worst case, if I want to try to find 993, and this is going to go through each one and try to come over here. Okay. A more efficient algorithm is binary search. Okay, this is one of the kind of considered one of the most efficient search algorithms. All right. You'll find some different variations of it, but we'll start with the basic one. What binary search is, it's suppose you have a dictionary, okay, like a book dictionary, all right. You have, let me erase this part. Right, and then you have a dictionary, okay, from A to Z, right? That's what I want to find a word which starts with M, okay? What you can do is you have a dictionary, you just flip it open from the middle, all right? And then let's suppose you end up with M, okay? And you're trying to find M. Now you're like, well, I flipped it open and opened on the page which have the words with F. I know now all this part of the dictionary is not valid anymore. I don't have to worry about that, right? Because I'm trying to find a word with M, it doesn't exist on this side of my dictionary. All right, what am I going to do? I'm going to look for this side only, right? So by this method, I have kind of divided my search into half already, right? Versus if I was kind of trying to do this, I'm trying to find M somewhere, what would I do? I would start with A, then B, C, D, E. Takes a lot of time, right? It's kind of easier. I flip it open. Oh, this is, if it was something over here, I know I can discard this, right? Now I have the half. I could do is, I can again flip open some page from that part, okay? And let's suppose if I end up with P, now I know that anything on this side of the dictionary I don't have to worry about, okay? This is what I'm more worried about. Okay, now my data set is kind of getting reducing. It will keep on reducing until you get to the words that start with M. Okay. And this is the exact concept of binary search. Okay. Binary search, what we do is we have a set of numbers similar to linear search. Suppose I have 3, 5, 7, 15, 20, 25, 50, 90. Okay? And I'm trying to find, let's suppose 20, 25. Let's take this one. Okay, I want to find 25. So I have 1, 2, 3, 4, 5, 6, 7, 8. Okay? Let me add one more. Then we'll come back. Okay? What I can do is I can take this, kind of divide it into half, right? And then 1, 2, 3. Look for the middle one. Look for this one. Okay? I've divided the array into half, and then I picked up the middle number. So right now it's 20. All right? Now if I have 20, I know anything before this is not valid because 25 is after that. Okay? The number that I'm searching resides over here. Okay? Since this will end, let's pick a different number. Let's pick 90. Okay. Now my data set to search is only this half. All right. Now I'm going to again start from here. I'm going to take this, divide it into 2, and pick one number, and then see whether it writes to the left or the right. Let's suppose I divided it into 2. This is the number that came up. Okay. Yes.
So it seems like in either case, whether it's like a dictionary or number seven, it seems like you have to do algorithms first before you.
Excellent point. Excellent point. Why you stole my thunder? That's what I did. That's okay. We'll park there. We'll come back to it. Okay. So now I'm on a 50. I'm searching for 90. I know it doesn't fall over here. It should be over here. All right. So I'm going to discard everything before here, and I'm going to start my search over here. Eventually, I will come back. I'll come to 90. Yes.
Is this the same thing as setting parameters? So look for the number 90 between like 50 and 100. Is that what this is?
Look for the. Say that again.
Like look for the number 90 between
Okay.
like 50 and 100. So setting one high point and low point. Is that what it's doing?
One more time. I still didn't understand. So this is similar to. I'm searching for the number 90.
Yeah.
Okay. So this is similar as what?
Like if you set like a lower number and a high
Yeah.
number.
Yes. Yeah. That is exactly what it is. So, but I don't know from the computer perspective. It cannot differentiate. It doesn't know what is this. What is this? Right? As humans, we can see and we cannot determine. But when the computer starts, it doesn't know if this number is greater than or less than this. Right now, when we begin, right? You can do a linear search and keep going 1, 1, 1, 1, 1, but that's kind of too long. So we have to come up with a better algorithm. And we came up with this is that, instead of searching this, we find the midpoint of this array and then compare and try to find out if it is greater than or less than this number. If this number is less than, okay, this means my number should be on this side. It's never going to be on this side. Okay? So I just have to search this now. Then I search for the high and the low, find the midpoint, and then I try to determine the same thing. And I say, oh, 90 is greater than 50 or less than. It's greater than, so it's going to be on this side.
So there's a bunch of binaries before.
Right, exactly. And that's where the name binary comes from. It's kind of dividing it into 2. That's what?
Like cuts it in half.
That's what?
Cuts it in half.
Yeah, cuts it in half. Yep. Okay. Any questions on this concept? As Gabriel pointed out, what's the pattern again over here? It's sorted, right? In ascending order. What if this was not sorted? let's suppose now my array has 5, 3, 15, 90, 2, 1. Will this work? Binary search will not work over here. It's going to fail. Will the linear search work over here?
Yeah.
Yes, it will. That's the drawback of binary search. It only works on sorted array. It does not work on unsorted array. Okay? But here's the mind-blowing part. That you can take this and apply a sorting algorithm on it, sort the array, and then use binary search to find that number. The result will still be better than using a linear search. Okay? There's a drawback, but from the efficiency perspective, you can use a good sorting algorithm, sort it, and then run binary search on it. It will still be better than what you would get. Not for 10 or 15. It's worse, right? Binary search is better if there is millions and billions rows, a lot of rows. Okay? For a small set, linear search kind of wins and you don't have to worry about sorting. It will work. But binary search works on cases where you have a large amount of data. And how do we measure the efficiency? I said it's a worst case, right? Now in this worst case, in the linear worst case, we had to traverse the whole thing, right? Now in binary search, if I want to search 91, I can probably do it in half the steps, right? I've already half the array. It's this thing, 1 step, 2, 3, 4. But I can do it in 4 steps. Versus the linear would be 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 steps. Okay? So binary search is good for large amount of data. Let's see, I want to search 93 and I do a binary search. So start with this one. Okay, what happened? Started with 0 and I went to the last one. So this is my complete array and I'm going to divide it into 2. 0 plus 31 divided by 2 comes out to what? 15.5. But we will use this operator. It kind of rounds it off. It only gives the top part. So it's going to take 15. Okay, so 15 is my midpoint right now. So next step is it's going to compare and see 993 is greater than 426 or less than. All right. So it's greater than, so it's going to discard the first half of the array and it's going to come to the second part. All right. So the algorithm is checking if this number is greater than or equal to. Equal to is important because the number that I'm searching could just be this one also. That, remember, equal to is important over here. Okay, so it says, oh, this number equal to or greater than, it is greater than. So I'm going to discard this. I'm going to move this point to the next half of the array. Okay, now I'm going to say index number 16 plus 31 divided by 2 determines this, the 23 index is going to come here. It's going to see 829. 829 again is greater than 993. So it's going to discard this half of the array. It's going to come to this part. Okay. 24 plus 31 divided by 2 comes to 27. It's going to check 993 greater than, equal to, is still greater than. So it's going to discard that part. It's going to come here. 28 plus 31 divided by 2 comes to 29. Going to check this one. Check this one. It's going to eventually come here. Okay. It's going to add this. It will come here and it's going to find this.
This will work. Obviously, it can work on a smaller number. Right? Well, it's not
higher numbers, like greater than versus less than is all right?
He's talking about if you need to find 5.
Yeah, well, let's run for 5. Okay, so for this one, let's complete this one. It doesn't show me the number of steps. I thought there was a, I think it might be a different one. Let's see if I have a different one. Okay. It doesn't show the number of steps that I was looking for, but you guys can see how many steps it took. 1, 2, probably 3, 4. Again, 4 or 5. Okay, in 4 and 5 steps, I was able to find the worst case, which is 993. Now, should I run this for linear search? I'm gonna wanna sit through this and see. Okay, you see what's going on. It's going to go through all 31 steps. All right. I'm going to stop here. I don't want to sit through the whole thing. All right. So from 31 steps, binary search only took like 4 or 5. All right. The question was if I'm trying to search, let's say 283. I know 5, but let's do 283, and it's going to serve the, oh, what happened? Refresh. 283, and it should come up with the same. Oh, it refreshed. Okay. Let's search 220. Okay. So it starts with this. Andreas determines, finds the midpoint, same thing. This time it's lower. So this one is going to go up now. Okay. So you have 2 points in your algorithm. One is low and one is high. Okay, high point. And depending on what you're trying to search, either the low index or the minimum index moves, or the max. In this case, since our search lies on this half, so that's why I don't want to change this one. I'm going to change this point. Okay, this time it lies on this side, it's going to come on this one. Okay, so both the minimum and the maximum both are moving, depending on if you're trying to search this part of the area or this part of the area. Okay, got it? Any questions? What if I don't find the number? If I search for a number that doesn't exist?
I tried that and found the closest one to it. I was just curious.
Yeah. Well, it shouldn't find the closest one. It will just say it didn't find. I mean, it stops over there in the animation, but that doesn't mean it found it. It should say it. What's the end condition? You will keep doing this until you reach a point where, you reach 776. It should be here, but it's not here, so it kind of stops over here. Okay. So it will come to the nearest one, and we'll see. Oh, it came to, as Eric was saying, to 777, and it said, well, it doesn't exist. It still keeps going. Why did it stop over here? You see these numbers? It started, the low started from this side and the high started from this one. If the number is not found, it's going to stop when the low crosses the high. And the low point, the blue one, crosses the yellow one. That's the other stopping point. Okay? We don't want the low one crossing the high one, or the high one going less than the low one. So that's one of the conditions also. Alright? Keep that in mind. Your minimum index cannot go beyond your higher index, or your higher index cannot be less than your minimum index. Okay. Okay. All right. Any questions? What questions do you guys have for this one? Okay. So what are the steps involved? Okay. I'm going to start with a minimum index, or you can say start index, low index, whatever you want to call it. This is this side. And then I'm going to start with a max index and or high, whatever you want to call it. This is this one. Okay. And then I'm going to divide my array into two, right? So I'm going to get a midpoint, which is going to be my my low and high index divided by 2. So this plus 0 plus 31 divided by 2. Right? That's going to be my midpoint. This is going to be 15, and that's the one that I'm going to loop to. When I get to my midpoint, I'm going to check if the index, the mid, my array I mid, right, is greater than or equal to, or you can check equal to first. Okay, the number that I'm trying to search, let's suppose is called num. The number I'm trying to search, is it equal to this one? No, it's not. Okay, or then I can add one more else saying if this is less than. If it is less than, then I have to search this side. Okay, so if it is less than, what's going to happen? My low is still fine, but my high is going to move over here. Okay, and if it is greater than, then my low has to come over here, and my high will still remain the same. Okay, I know it's still kind of fuzzy. Anybody, any other brave soul wants to take a stab at it? Now you want to try? You want to try? All right.
Will's got this. Boy, how many lines can you use?
Oh, I got this. What was that? How many?
How many lines can you use?
How many lines?
Use all
So
We'll start
with
off.
algorithms too. Yeah. So let's start with the same. You have a function. You have an input number that you want to search, and you have an array.
Roy used ES6.
Yeah.
Already failed.
You said 6 lines, not 6 characters. Calm down there.
No, I said use ES6. I said use the
Oh,
ES6.
yes.
We're giving him a hard time. One of the more difficult algorithms to write. Yeah. Yeah. Yeah, that's fine.
Yeah.
Yeah. Okay.
So I just wanted to use my name, same variable name. So I put find num, but that's the function.
Oh, I see. You guys happy with ES6 now?
All right, you're done.
So let's min num equals 0. Let, because I know he's gonna call me out on it.
Initialize your variable.
Max num equal. No, because these change. Oh!
Start with constant as it changes.
Metamorphosis, go. Min 0 for now. Just so it's declared.
Okay, you guys got it? So we started with the first and the last one. Alright?
And then this one's going to be while. While
Yep. So you want this to be true. Yep. So guys, see this statement? So this is what we are trying to consider. We are making sure that this doesn't flip. We want to keep continuing. We want to run this until our minimum, this thing is less than our I index. Alright, as soon as they have flipped, that means that they have crossed and we haven't found a number. So we want to stop.
I don't remember what the command is. Math dot. I'm just gonna say floor.
You can just add and use the slash. Is still going to give you the round off number, the top
Okay.
one, the divide one. The mod one kind of gives you that, but you can just add 2 and divide by 2 is still it will give you the higher. Remove the decimal.
Num plus max num divided by 2.
Yeah. So this will still give you the whole number. So 0 plus 31 divided by 2 is 15.5 is going to give you 15. That's why it stops over here. And half, and then stops at 7. And keep going. Okay.
If R min num
So we are at this point now.
is less than num, then we want to move the, if it's less than, we want to move the max num down.
Okay. Yep.
Is equal to min num minus 1.
All right. Hold on. So you guys see. So now let's suppose I'm trying to search 434. I start with this one. I halved it. I come out here, right? So this is my index,
Yeah.
right? So I come here. What's going to happen over here now? So I'm trying to search 434. I start with this, correct? I halved it. It comes over here. It says index this. So it's going to check is 434 is less than num. Is it?
That's what I'm doing here. R min num
Right.
is less than number.
So I'm trying to find 434.
The reason why I'm doing this because I was thinking about that.
Okay.
If you're checking every single time, because there should only ever be one point where you're actually going to equal,
Okay.
why are you going to check it for every single calculation when you're looking more for less than or greater than, and then at the final one you can do an equal, because that should only be checked once.
Okay. So if you don't check over here, what's going to happen? It's going to move the midpoint here, right? So you when you skip this number, So right now you
Well,
found that
no,
this
because
is
if the number equals, because I'm just doing less than,
Right.
not a less than equal to.
Yeah.
If this number is equal to it, then it's
Okay.
going to skip that and go to the next check.
Okay.
So the other checks would be else if our mid num is greater than num, do this, and then else if our mid num equals num. And my thinking was just solely the fact that since this only needs to be ever true once,
Mhm.
instead of checking it in the worst case scenario, like we said, we'd have to do it 5 times. That means you have to run this one 5 times before you actually get the answer. Whereas if you do it this way, you only get it once. So in my mind, it was saving a calculation.
Okay. Yeah, go ahead.
Okay. Then there's our mid number is greater than num. We want to move the min up. And then if the number equals, we return mid number. And then out of this, if it doesn't, because it's going to come in here and check while this is true. So if it doesn't, then it would return whatever we want, -1.
Okay. Yeah. All right. That's it. To be honest, I wouldn't have been able to implement if somebody asked me. I know the concepts kind of takes me a while to whiteboard this thing. I need a lot of practice before I can reach this. But really good job on implementing the binary search algorithm. And this is what the algorithm is. All right. We are keeping check and we are moving our indexes. And then until we find the number or we return some negative number or something that doesn't exist over here. Okay. Thing to keep in mind, it only works on sorted numbers. If they are not sorted, it's not going to work. Binary search cannot work on unsorted numbers. All right, that's kind of the drawback. But again, as I said, it's worth it even if you use a good sorting algorithm and then use binary search. It's still more efficient than using linear search.
And then search the binary tree.
Yeah.
You can write that code.
Yeah.
I will, less than that.
Yeah, we're not going to look into binary tree. That's even more high level. That's like the next level. But you will see some variations for binary search. Yes, go ahead.
I was gonna say, I thought when you were doing binary search, I thought it was just like ones and zeros.
Oh, okay. No, this binary is like half.
Okay. It's a true or false.
Yeah, true. Yeah.
That's how I was
So I select this out. Here's another really good website that kind of. Let's see if I can find. Binary search tree. That's not what I'm looking for. Okay, I want to share this one. We'll see this next time. All right. Let's see if I have missed anything else. Okay. Any questions on this? Okay. I want to show you one thing, and so this thing you guys are going to look at on Saturday, but let me just show you guys. So when we measure these this is how their graph comes in, right? These are kind of calculus thing, the log part, all right? Log from calculus, that's how these algorithms are kind of measured. And binary search is this one, log n1, right? The O over here is called big O notation. You guys will see this on Saturday, so I'm not going to go into detail, but what I want to show you is that this graph, the blue one, that's the graph for binary search. All right, what it means is your y-axis or the vertical one is the time it's taking, and n is the number of elements in your array. Okay, now if you look at this, and this your green one, this is your linear search. All right, so when the linear search starts, you can see linear search is better for until this point. Okay, so for this number of sets, it takes this much time, but your binary search kind of takes more time. All right, so binary search, linear search is better for like smaller set of data. All right, but for a larger set of data, you see how the time complexity goes up. It's taking more time for this one, and binary search kind of stays, and it will go to infinity, but it will never go above a certain point. All right, it will never reach that point, but it will never go above it, and your linear search will keep going up. All right. So to give you a visualization, that's why linear search is super inefficient when it comes to larger data set, and binary search is one of the better ones. Okay, you see this one, O1, that's kind of ideal situation that you can come up with an algorithm that takes, it doesn't matter how many number of elements you give in, it always searches the result in the same time. That's kind of like the ideal situation. I don't think there is anything that exists. But this is this thing is the closest one right now. So log n, any algorithm that you see, and you see the word O log n, that's a more efficient algorithm. Okay, you will see this more on Saturday, but I just wanted to show you some visualization. All right, any questions? Right, so we saw searching. On Thursday we'll look into some of the sorting algorithms. Okay, these are kind of more complex than searching ones. All right, we'll see like 4 or 5 ones. We'll start with some of the basic ones, and we'll look at the more efficient ones. But those are kind of more difficult. It's going to be a little bit more tougher class than this one, because those are a little bit more, they require more, not just the coding, but understanding, and they're a little bit more complex than searching. Okay? All right, so we'll take a break, and then the rest of the time is project work. But since I already have one group that's submitted, come on, guys. Nobody else submitted anything. What's going on? All right, so you did? You didn't send it to me?
Oh,
What did you send?
I put it in the conference.
Okay. You can submit it. So let's see. So we'll come after the break, and then these 2 groups have submitted, House Lannisters and Targaryens. So you know what? I just want you guys, one of you guys, to bring your laptop, just connect to it, to showcase what you have done, and so that every other groups can kind of get an idea. And then if you have any questions, please don't concentrate on the product right now. If you have questions like, oh, how did you set up your board, or how did you divide your task, or how did you achieve this, how did you come up with your design, those are the kind of questions that I'm looking for. If you have those kind of questions, please do ask. Don't concentrate on, hey, how is this going to work, whether this would work, what are the products. That's for next week. Okay, before going on the break, okay, let's come from the break, do this exercise, and then I'll give you the final remarks, and then you guys can work on your project for the remainder of the time. Okay, I will convene back at 8 o'clock. We'll start with those 2 groups. You can come up and kind of share your details.
So if we're done, should we submit?
Yeah. You guys didn't submit it? Yeah. What? It's not good?
So, okay, I guess we need to solve for.
Yeah. Yeah. Something. There's no wrong or right answer to this.
This is